Hello, today I'm going to cover two different subjects, but they are somehow related. One is optical flow and tracking. That's chapter 7 of Zelsky's book, chapter 7. And then another one is stitching and panoramic view. That's chapter 9. Two are somehow different subjects, but related. So here, optical flow and the tracking means that frequently we see that there are motions, there are some changes, something's changing in the picture. Then how do we follow that, trace it, and sometimes improve it by the manipulating their images. So that is the main subjects. So first part that we're talking about optical flow and tracking. The chapter 8 also talks about dense motion estimation, but just a very small portion of them we cover. What is important in any kind of image is the motion or dynamics or kinetics. And of course, the movie of any kinds, animation of any kinds, is that there are changes in the picture, and we kind of feel that the subject is alive. So, by the way, the word animation, that animation is like a cartoon or some hand drawing of something moving. Animation actually means come to alive. Come to alive. That means that looks like it is alive. When you see just one picture, then you don't know whether that's alive. It's maybe that is just one fact only. But when it keep moving, just like my face there and moving, then say, aha, that person is alive or has a life. That kind of idea. So in a way that in computer vision, the motion or those dynamics or those changes, all meaning kind of the same, are very important. Then, of course, what happens is that when there's the camera and objects, and either object is moving or camera is moving, there is some kind of smudges or some kind of blurry. That is this kind of motion blur. So some part get less clear. So often that this is the dilemma or the kind of challenge to reconstruct it back to the original clear site. And this has been done pretty well over the past several decades with the algorithm, the developments. So you see that there's the motion wise that there's a slightly different kind of changes. Actually, this trees looks alive when you have a multiple shape. So let's look at the other one. You see that it is due to the wind that we see the shakes, and you see that up there is the clouds moving. Okay, so this is a 3-minute the video, but I'll just stop this one. So main idea is that we see in the picture that by the motion or some kind of a directional movement that we see they are belonging to same kinds or different kinds. So we see that there's the segmenting when we are doing perceive that they are the same group, different group, this to a different group. Those shape usually gives some kind of a cue about the sameness or differences. But also this dynamics, even if that they are all apart, that we kind of put these two things one group because they are moving toward the upper left corner, and these 4 pieces of dots is one group because they go same direction. So then motion, called the common fate, but same type of dynamics, is very important in associating the parts into one group. So again, that the similarity wise, there's a parallelism or symmetry or some continuity, and then there's closeness. There's a closure. So all is included. And then here again, the motion is very important in associating some pixels into one group. So the motion is very useful in estimating three-dimensional structure. So even if we have only two-dimensional the picture for every image we capture, but when you compose that in multiple sizes and multiple direction, then we can construct the back 3D motion. That's why the 3D digitizer that has cameras moving around, and by motioning, three-dimensional objects can be constructed. And then segmenting objects based on motion cues. So like people walking, then there's a head may be staying, but the leg is moving pretty actively. The hands, arms are moving also with the motion of those walking. But head is changing the location, maybe. I mean, changing the position, maybe, but still the shape or the relative shape stays the same. So anyway, we perceive the kind of the segments, that this belongs to head, this belongs to leg, this belongs to body by motion itself. And then to do that, we need the tracking and optical fields that we want to know, find it out, and the learning tracking dynamic model. So whatever that means, there's some dynamic model, some objects are moving. So how do they move, and what kind of a rule do they have? We'll see that example in this human walking and recognizing events and activities. So previously we had the example that the two piece of the image exactly the same, but there's one car moved from here to there, so that's the only differences. Then we say there is the traffic moving from left to the right and some moving right to the left, so you can trace those traffic. Then we can improve the video quality. That is that when it is being done automatically these days, that all done in the video camera. Some of video camera you read that motion stabilization. So even if you are shaking or car is shaking, or because you are taking the video while riding a car or some moving objects, still so the camera itself cannot be very stand still in the same location, but when taking picture, that it just compensates the motion of the camera and then actual pictures, because there's a sensor within the camera that goes with the motion. So with that data and then outside data, you do the adjustment. So even if that is a little bit shaky, or people take a camera on their shoulder and walk and take a picture, still you don't see those kind of jumping motion. So here the perception is pretty much kind of naturally built. So in here, all we see is that we see each point is moving. Actually, only this point is staying still, and all the others are moving. So like one here, one there, like that one. So even if they are moving, but what happens? So looking at that, we feel like it is somebody walking, isn't it? So somebody is walking. So this is a head, this is arms and the legs, and this seems to be body. So that visual perception of a biological motion. So this one is a thing called the motion capture. So this one is a visual motion. There is a technique called the motion capture, used very extensively in movie making or in sports medicine, where how people are moving. So you got for a human body, there's a few white kind of a marker. Sometimes this can be a cotton ball pointed in there. Then let this person walk. Then each of those the movements of those dots are they are recorded, and all those data are saved. And using that kind of tracking, you can generate the motion of how those person will walk. So in many occasions that these days almost every movie is using CG or computer graphics, where that there's only one or two real person and they are doing this kind of action, sometimes just a regular walk, sometimes crawl, sometimes run, or sometimes jump, like a few of those action, and those motion pattern is saved as a data, and you can simulate the shape of that person added to, and it looks like some people are walking. So here we see those stick figures, that those dots and lines moving, and then just giving some. Hopefully you see those the blue lines are what the shape of or the trick of the hands movement, and then those green one is like a knee part was thigh part, and those red one is left foot, and those the purple one is right foot, like that. So you are just adding some more of the body and the clothing and color. There's like a person, or one person or two person walking. The another example being used is this one. I don't know whether I can make this one run. So in this case, that we have those hands and the finger simulated, and this the scale. So it's supposed to that show you how to do the playing. So anyway, this can be played. I don't have the video file, so I cannot show you. Anyway, that is being done. So motion field is the kind of a term saying that where in the picture some movement is recorded. So here there's a round table. This is a spinning, and there's a cubic. What's a cubics is sitting on here. So when this is turning, you see that this one was turned a little bit. So the amount of changes on the this actual rubrics or the Rubik's cube, Rubik's cube is showing with the changes, and this one spin. You see that those texture and those kind of texture changes. So the others, they didn't have any changes. So only in the whole picture of a frame, that only those area of the pixels that has been affected by movement is recorded. So we know which pixel, and later then how or in what direction they are moving. So motion field, that's called the motion field. This is a motion field. You know, also this is a pixel of a size like 800 by 600. I know it's usually it's much bigger than that, but that, and of them only those pixels are affected by motion, and then motion the direction, detail of those motion can be figured it out or recorded later. So motion is field a projection of 3D scene motion, 3D motion into the image, and there's a model that has a optic flow. When this is turning this direction, then we'll see the dots or same point on here will move here to there to there. So we'll say that the angle, the direction will be to this one. If it is the other way around, for whatever reason, this is turning the other way, then we'll see that each pixel will have a different direction of flow. So that is called optic flow. So motion field and the optic flow are closely related, and sometimes people use interchangeably. But there's a clear differences. Motion field is the sets of pixels in the image that is affected by motion. Then optic flow is that the tracing of those individual pixels to the direction it is moving to. So here, this is the flow. So the motion flow. So suppose this, I don't know, so this is monkey or some kind of a robots, and this guy is going into, in other words, that they're jumping into this wall. It is just pushing its head into that wall. Then every point will look bigger suddenly, so get closer. So each point will show while it is moving, they're coming away from those the observer, that monkey or the camera of the lens of the camera. So it is looking into this somehow on the left, the right hand side of those points and moving into there. Then the points will look like it's moving away. So that direction is the optic flow. Optically looks like they are going away. And then here, that this in this example, that this animal is turn around. Then in a way that around in here, we see that some of the objects look they're going this direction because it is turning like a counterclockwise. So we have the screen that is measured by actual centimeter like that, and by the motion of that object, or in a way camera moving, that we see each pixel of that the image is somehow changing. What used to be here, say for example, will go away. Then the closer to this point, it may have more of the movement, and the farther away, it has less movement. So that is optic flow. So to model it, we got to specify this into actual model. We had this one before, so we say that this is the object, and then there's a light source, so shining the lights. Then we viewpoint here, so sometimes we give this kind of a picture that we are looking at from here. Or this is where human eye is, or the camera lens is. Human has two eyes, but in this case, we just see one at a time, so to speak. Actually, the way we have the two eyes, that the left eye and the right eye sees different things, and that somehow in our brain they compose into stereo vision. So anyway, so by doing that this is the object, and then we have those in a way that because of a light. If there's no light and completely dark, then we don't see anything. But because of the lighting and those the objects or the surfaces, in a way that light got reflected back, we see it. So the amount of those seeing is the modeled as the ray, or the kind of the so-called view vector that goes in here, and then that being we cannot see in the sky or in the thin air, so we need some kind of a screen or some kind of what can I say, the screen or some display surface that's showing into that this object and to the eye, and that we're intersection, and then every points over there forming same the shape and except that because of this relative position, this will be smaller than the real object. But of course, that if the object is around in here and the projection plane is here, then the projected image will be much bigger than real objects. So anyway, so we need in the projection part the light source, that's the location, and then the right ray that goes in, that's called the projector, and this one is also called the projector because that we are putting projection from here to there, like that one. Then projection plane, this is a projection plane, and then objects, and then viewpoints, that's the way we have it here, and aperture, how big we see it. So in a way that this view plane, the projection plane size is our aperture. For whatever reason, this is the window, then we'll see this much. For whatever reason, this get the smaller, the small sizes, then we'll see portion of this the objects, and we don't see everything. It's like a huge building outside, and when you sitting inside your apartment, then you see just a portion of them. So all those parameters are needed to model it. So what we need, when we are seeing from the scene outside, then we do it by instinct. But in this case, that we see that we got to simulate everything inside the computer, and we got to make it into mathematics. So everything must be parameterized, and we manipulate those numbers to make those the value changes. So in a way, computer vision is the way that real world, that kind of a nice or ugly scene become numbers or data, and that data got manipulated for the understanding of the object. And when that data is put back into display, then that's computer graphics. So data to the image, that is computer graphics, and the image to data, that's initially the image processing, IP, and further understanding and the identification, then it is computer vision. So motion field and parallax is, so what we have to think about is that, okay, motion, then yes, it's a vector. So we are very familiar with that, that we have a time here, and each point, say, suppose that we got just the one-dimensional the movement up and down. Like a good example is that the temperature thermometer, those go up and down, up and down. So in the morning, those very cold, so minus say 10 degree. Then as morning comes in on around the 5 o'clock, I mean the 7 o'clock, it becomes say 0 degree, and it gets a little warmer, so 7 degree, so on, so on. So it has all those numbers. So this one is minus say 50. That's lowest it can be, say, and then there's a highest to be plus 50. So it will go up and down. So go up and down. But how? By time. So this is like 4 a.m. and then this one is 5 a.m. and 10 a.m. or whatever. So this 3 p.m. So on. As time passes, then how does this one changes? That is our the dynamics. So the dynamics is obviously the changing of the location. So when at the time t that it is here, and at the time of t plus delta t. So if this is 5 a.m. and then this one may be 5:10, so 10 minutes past, then where these dots are, like a sun is moving, where does it too? So that kind of the moving 3D points. Then how fast they go of course, it's dx, how much of it changes, this whole thing. So this one's two-dimensional thing, location, and then the time. So it's a partial differentiation with those time, respect to time. And then this xt of xt, yt is a projection of x in the image. So the where is moving up like that, then x value is changing from here to here. And in this is an image plane or image world. This is a real world, and they are showing. So apparent velocity means that what they perceive is here, isn't it? So real plane, the real changes are over here, but what we see here is only this direction. So if this took 10 minutes, and then it went through, say, I don't know, so the 10 kilometer, I don't know what kind of the car or thing, it will go 10 minutes, and it's 10 kilometer, 1 kilometer per minute. That's very slow. But from our standpoint, our view location, of course, that distance from that object to me, that's what matters. Then what we see is that this is our window. Then because of those distance is like 1 centimeter, then it took the same time from moving from here to here, but that same time from here to here. So this will go definitely very slow compared to this one. So this one is apparent, or our perceptive the velocity. So you know that you have that experience all the time when you say they stand up on a big building on the top and you see the car moving, then they go from one location to other, and you see that moving around here, and you see that they are going much slower than real objects. Or looking at the airplane, they're moving very fast, but it goes like that, very high up there. I think it goes like that, but in reality, they are flying like 100 kilometers per hour, like that. So it's much faster, but for us it's very slow. So that kind of a thing that we got to correct those differences between the real movement and the way we observed. Why? Because all we got is those image we captured. So that's again saying apparent, look like apparent, what it appears, what we perceive. That so whenever there's a motion field and this movement, then we got to consider what is that object in those display. So this kind of area that some part this is moving, changing, those fields are known as a motion field, as I told you before. So the motion field that goes we have those changes, how much changes that has been. So from movement here to here, and then xt, x, t, dt. So this big X is a real world, and the small x is what we see as kind of a display. So big V, large V is a real velocity, and small v is our perceived or apparent velocity. So there's a relationship of those, it's more like the law of triangle. So the farther away, then it'll be slower. There's no problem. So we put those x and the y in separately. So very important is this z value, z value, because z is distance from the person or the observer, camera, to the actual object that's moving. So the motion v, the index of 3D points at the z. So how far off we are, that makes big differences. Then so pure translation wise that the motion is changing. So when they are moving, then it is changing from one location to the other. So x and y they treated separately, and depending on the speed that we know that new speed is coming. So you will see that those things are moving up and down. That so object in the distance far away moving slower than the one closer, isn't it? So the one near here is moving much faster, but the other one is just very slow, much slower, isn't it? This is something that you are experiencing every day when you are the riding bus or the car and go to in the city is very hard to see that one, but when you see go to this country road, then you drive, then the trees nearby or around the road is moving real fast. So it's passing like that, but the mountain on the way out there is going much slower, but they're still moving. But look at the sky, that there's a sun or moon in the sky. They seem to be exactly on the same position because the distance is so farther away that any kind of changes you're having. So in other words, that this is the object's location, and you are moving from here to here. The size is actually the angle between this one, and then I cannot draw the line like that. Sorry about that. So this angle, the bigger is the angle, we see it big. The smaller, we see much less. So this is the distance that we can perceive, and very slow when it is far. So in astronomy, for example, that those angle is so low. So you know that 1 degree is, of course, a full circle is 360 degree, and then one is that just 360th of that, and the 60th, just like a clock, of 1 degree, the 1/6 degree is 1 minute, and 1/60th the minute is 1 second. There's why the name goes like that. But so in this one is is 360, because 60 times 6 is 3600. So one degree is very small, and 3,600 of them is really, really small. We don't see any differences in naked eye, but with the instrument these days they do. So when the Earth is moving around, or the solar system moves around, and the distance of those stars, so we measure the distance from there to there, from like July and let's say January, then 6 months they go around the sun quite a bit of distance. Then those things is a way that how to calculate those distances, and usually it's 1 or 2 seconds. Well, the 1.0 to 1115, very detailed or the large number of those decimal points, so we got the accuracy wise, and we can calculate this 500 light year or the 1000 light year, like that. So in the length of the motion vector, those distance motion vector, is inversely proportional to the depth or distance. And so that's what it is, that there's a train is passing, and you are standing, then you see it's so close that you see this, you don't even see the detail because of that fast movement. So, but if we move out to on the street or some other places, then you see that they are moving. Okay, so the VZ, when non-zero, then every motion will be okay. But if VZ is 0, what does that mean is that if it is parallel to the image plane, in other words, that we don't see any movement, in other words, that the distance is 0, then we are in a way going together with that object. There is much of distances, the Z is. So we don't see that when we are part of this train, then we don't see that any movement. Well, good example. You are on a train or you are on a car. So inside the car, so it is running real fast, driving very fast. But the kind of seat or those lighting inside the car, you don't see that they are changing. They are staying in the same place, except everything else is outside is moving. So when the distance between object and yourself is at the same location, then the speed is 0. That is what the Einstein's relativity also says about it. So anyway, that's what we're talking about. The vision fields as optical flow is that apparent motion. How do they move or brightness changes in the image? So the flow must be same as the motion field. So this optical flow is how those the value changes as the motion occurs. So if the flow and the motion field must be all same, but sometimes depending on the angle, depending on the discrepancy of the speed, it may not be exactly the same. So apparent motion can be caused by lighting changes without any actual motion. That is, that sometimes because that the light changes when farther away, then looks fading. The farther away, then it looks dimmer, or the intensity is lower. So when things are moving out, then you feel like they get dimmer and dimmer. So even if that's the same object or same pixel far away, because individual pixel you don't see it, but if you make that one is very the kind of the intensity got lower, dimmer, then looks like it's going away from us. That's happening, and the uniform rotating sphere on the fixed lighting, then they keep changing. Then the other side looks the dimmer. So here, motion field and optical flow wise, that this the black square is moving to this location or this location. So moving this location, then those fields, because of those area is moved over here. So those fields area of the pixel are changing. This is the motion field. This is motion field. Then we see that those somehow those little pixels over there looks like stretched out. So the better illustration is this one. This is the airport runway. When the pilot is trying to land in this airport, this is a runway. Then this is where you're gonna land. Then you start the driving further. But the landing in here, then everything will be going away from you. So all those individual value or the little object looks like going past to you. But if it is not landing, but you are just passing it, then obviously they will be moving it out away from you. But actually, it is more like motion this direction, then they seem to be going away from you. So those motion field and the optical flow is that individual object looks like moving from here to there, moving from to here. So airplane is moving this way, and then every object looks like going away. So always the camera and objects are contradicting each other, or they are away from each other. So when a camera is moving, that object looks like going away. Camera coming closer, then looks like they are moving this direction. So same way it goes. So estimating optical flow can be that for individual pixel, the direction and the vector can be determined. So in here, that this one is a sphere, and the sphere is a spinning like that one. Then we see that this area has most movement, the spinning here, and then this outside is also showing the movement. So because of those nature of the circle, that we see that here we see this thing is spinning, so it goes this direction, and the other points looks like going in on the from our center. It looks like going away. Same thing goes in this left-hand side, right-hand side, same manner. Okay, so the brightness constancy constraint. So we want to change, or that we want to have our brightness being changed or the stay same. So again, the brightness or intensity changes are the way of understanding, or the giving us the data about those motion, and the motion field can be expressed by those pixel intensity differences. So I'm not going to go to this one. The brightness constant is that the x direction, y direction, and some initial constants that goes together. So that equation that actually gives how much changes in the intensity on pixel U and V plus the total illumination. That is sometimes it's called ambient the lighting. That background lighting is there. So you have those changes, and then the current intensity, and we say that we say whatever changes and the original the intensity, they must compensate to 0, but not necessarily this is true. So anyway, the brightness is we can make this brightness the constancy constraints being as a way of modeling our images, or actually more about the video type of images for understanding those changes or motion. So gradient goes this way, and direction. Okay, so but there's a issue about that the aperture. Aperture is the opening, in a way, window. So aperture issue is the size of view windows. So when it is in a small the sizes, then we see that those purple one is one was here and one was there. So by that we feel like something is changing. So we draw this line and erase it and draw here like that one. Then we see it, even if that is two lines drawn in sequence and that there's no motion, but we feel like this line has jumped over, isn't it? So that's the small the size of a window. That when depending on the aperture, that the effect, or sometimes that the illusion can occur. So illusion by aperture problem, that if it is too close enough, then actual motion goes this direction, even if that, so actual motion goes from that direction, then this two the drawings look different. So that difference can be shown like that. So what happens is here, that all it does is that it is moving down. So we see that this white part is we are drawing, and erase, and we are drawing like that. So, but still, we look like it is really moving. So we draw, erase in a sequence, but they look like really moving, right? but it's in a small case, they are small opening that we don't know how they are moving. But if we have that in a vertical direction, then it's still moving. So those strips are those dark and light, bright. The lines are moving. So we are moving like that. But don't we feel like there's something spinning? So it is something is spinning, turning around. That's what we may see. So we say something goes left to the right and turning like that one. So this is an example like that one. You have seen this kind of a thing often. So when you look this one very carefully, then it is not really spinning at all, but it is just the drawing here and drawing here up up that kind of direction, but looks like it is turning on the counter there clockwise. So it's turning like that. So that is called barbershop, the illusion. So by that, so depending on the size of those aperture or opening of those view, that sometimes we get the wrong idea of whether it is spinning or not. But it can be corrected by calculating the gradient. So you give those motion into the matrix and solve for u and v, and then it is the kind of intensity differences at the time on the different pixel location. So don't you see this one as a form of very similar to the eigenvector thing? So we see that this one is original data of the pixel in a matrix, and then somehow that we derive a u and v vector and this vector. Of course, there may be some lambda here, but you can actually, lambda is the single value or the scalar constant value, so we can multiply this one, then this lambda can even be hidden inside in here. So anyway, this Lucas and Kennedy, they also did using this the solving method of those eigenvector, eigenvalues. Then it could solve those motion problem and find the more idealistic or more satisfactory results. So if you keep doing this one, then you can change it. But if you got the vertical, straight edges in here, then there's not much of improvement because of the difference. There's no motion to be detected, isn't it? You don't know there was going around or not. But this way, if that goes from here to keep moving like that, then it's much easier to detect the motion. So I'm not going to go to the detail, but the idea is again each pixel and have some vector of intensity that you solve it, and you got the most consistent the information you can get. And then there's the Harris detector. I showed you, explained those Harris, the corner detector, and we actually have those OpenCV program that actually checking on Harris the corner detector, and they also using same technique. You don't have to know exact calculation because all you have to do is just calling Harris corner detector. So that's the eigenvector, eigenvalue that you just manipulate. So that's why I say the eigenvalue and vector is so important that huge amount of data can be they reduced into vector of certain the sizes, and that gives kind of a uniqueness. From here, they reduce into smaller sizes. So when we are doing the feature detection, remember that we need that detection in the last chapter, that you can generate actually two lambdas. So remember that if it's a 2 by 2, then there will be 2 lambda values. And if it's larger, then we can get more lambda value. But somehow there's the smallest, you sum it up into groups, then it can be just for the element 2 by 2, the vector, the matrix. So you can have up to 2 vectors, eigenvectors. So I kind of explained that the derivation of the eigenvector and eigenvalue to lambda. But real kind of a good thing about is that using that this method of kind of the algorithms, that you can easily see by this each scene each pixel location you are calculating this eigenvalue and eigenvector, and compare these 2 lambda values, and the edge is that lambda 2 the second one is greater than lambda 1. That's this small one, and they are much larger than this edge part. And if it is a lambda 2 and the lambda 1 and 2 are very large, then this is a corner. And then the edge is that lambda 1, this is lambda 2 or 1, and the 1 or 2. So one value is much larger than the other one. That is the edge. And then both are very small, lambda value very small, then that's flat region. Actually, that means that there's not much changes inside. And this one has drastic changes. That's why it's a large value. So remember, when we are talking about feature detection, there are 3 features to detect. One is corner points. 2 is edge. Third one is region of the same property. So here, look at here. I showed you this picture before, and then in this house and the tree like that one. So you go around and see where is anything that is the corner or any edges or any the flat region or area. So you see here, so gradient calculated, and the lambda 1 and the lambda 2 lambdas, eigenvalues we calculated, and both are very small. This is a 3.15 and 2.71, like that. So very small. Then this is the gradient. Those things are the small magnitude, and in this case that is a uniform. So they are not much of dynamics or kind of changes. So we call that on ill conditions. This area, nothing very interesting, but of course that we're going to extend that on until we hit something interesting. So when, as I said, they both are small, lambda values are small, then it is on region, it's a region or area of sameness. And here gradients one dominant direction. So when it is lambda 1 and the lambda 2. Oh, actually, by the way, that in case that I think it's a good idea that this lambda 1, the eigenvector, the lambda value is going this direction, then each vector can be, we are going this direction, then each vector has 2 components. One is horizontal direction, and there's the vertical direction. So if this goes very steep like that, then we got this is a lambda 2, and this is a lambda 1. So in the case that lambda 2 is big, but lambda 1 is small. So like that, so those gradient-wise, that the one is large and the one is small. So this way, or we have a very much like that, then we have a lambda 2 is this much, and the lambda 1 is this long. So in the case that then we have a much larger, then the lambda 1 is much larger. In this case, the lambda 2 is much larger. In the case that it is it's more like edges. It's on edges. Then these points. So this system is lambda 1 is very large, and the lambda 2 is very large. So we got very much changes. In other words, that both in x and y direction, something's big, something's changing a lot. And here's another different value. So in the case, we call that well conditioned because of the fact that they are showing big changes or movements. And so they both lambda 1 and lambda 2 are large numbers. Then we say, okay, this is edge detection. What that position is edge feature. So there's a few errors. This one goes too detailed. So if you are interested, why don't you read the book? That's a very irresponsible way of saying that. But then there's a C, Thomas C. She is actually the Chinese the researcher, and Thomas C. Two people talked about how to use those whole thing combined into matrix and using that as the calculating their eigenvalue, eigenvector. So we talked about motion, the motion field and optical flows. So we have a certain area of those pixels that are affected by those motion, and they also have vectors or changes. So that direction or that magnitudes are our motion. This optical flows. So how much of the optically diffusible is changing, but that can be happening either camera changing or object moving. So in here, camera is stationary in this picture. Camera is they are saying, I'm just taking pictures. So actually, if somebody wants to take picture on this lady, but there are some people who's not part of this image, and our intention was just walking. So there's a blur. So object is blur. For whatever reason, you wanted to make this person's picture clear so that we can identify who they are, maybe it can be done. That is what we are talking about now. In this case, there is the camera, in a sense, is stationary. Actually, camera better be around in here. So this motorcycle is moving, and then there is another car exactly and driving exactly the same speed, so going together. So I can focus on this motorcyclist all the time. So in a way that the camera is staying, but the outside of this scene is moving past. So in the case that the object is moving, this object is moving, and outside the object is moving, and then the camera is also moving. So camera moves with the this motorcycle. In here, camera stayed the same, but the people or the object moved. Here, camera is moving, and outside things are not moving. Of course, that this moving object we want to focus on, so we are moving together. So that can be blur, can be corrected, because then we have a certain flow going certain direction. So all we have to do is just compensate it back. We have those matrix that can bring back those amount of the changes. So same thing here, that some portion got blurred, so we can move it back, and then we got much cleaner, the clearer pictures like that over here. So in fact, that this one is kind of a mirror image in here, but anyway, this one does. This technique has been on and being used by police that about even 30 years ago, that this is a picture taken for a moving objects like a car. So this is moving this direction, obviously. this direction. So what we have to do is just move back the pixels to that amount, and then we know the optic flow, the low, so this far may be moving differently from this much in terms of our perspective. So you move it everything back. So you got the license portion, partial of them be identified. From this one, you get this one. That's amazing, isn't it? Or in this case, that this one is very blurry and restored, not so good. So they close up, and it's the same thing here. And looking at them, everybody can read it. W193980 something. So easily you can identify. So motion blur can be corrected and used for the better identification. And there's a book called the Digital Image Processing. Actually, I have that book. But this one is the taken picture very much like that. Because the camera was moving. In previous case, that car was moving, camera stayed, but because of car moved, that we didn't have the clear picture. But in this case, the camera was moving, the book sitting on the desk without any changing. But somehow that from here, optical flow, we see that the direction is identified by those movement. We have those things. How those dark ones keep moving down by this streak, we can get those the vector. So we move it back that much of those pixels, then we got this. So usually what you do is you do multiple iteration. But if the pattern goes this way, then it does this way. And then you adjust a little bit because of those vectors. So you focus a little more on the x direction. Then you got almost the same, but somehow is different. But what if that it has a locally, the individually, instead of total direction, but this one is a little bit, this one differently, this one differently, then you get this kind of the adjustment, and almost you can read it. But even further, you do one more same technique, then this is very clearly they restore the original the shape of those picture or the cover of the book. And this one is another method, that least square filter, by having the filter and then they change those optical flow corrections. So you do multiple, it depends on how much of those. This is a least square filter, then what is the standard deviation, or actually variance size. So the bigger, then it is much wider, it's more blurry. But if it's 1/30, so we don't know which one is best number, so we try different one. Then obviously this works just fine. In 2 iterations, it restores the original picture perfectly. So that is a great thing about those least square method. I mean, those motion blur correction. Then in this case, that we have this. This is all motion blur. Then there's a car movement. So here, so it has been they taken picture while this car was moving. So we are just focusing on that, and from here we do corrections by intensity and those directions, and eventually come out with a much cleaner shape in here. And the camera moved, so the window is not clear, so you can do some multiple iteration and much clear picture of the window, and this location is taken care of with a clearer picture. So even if that this one you can still identify it, but you can make it much cleaner or much clearer images. So that is the de-blurring. The blur means get the fuzzy. The fuzzy can be reduced. So conclusion-wise, the image can be blurred due to various reasons, such as poor lighting, wrong viewpoints, or importantly, the motion of object or camera, or both. So motion blur can be improved by geometric transformation that reverses the motion. And there are many algorithms that facilitates corrections and improving the picture. So you do the other way around. Then this elephant can be moved, made blurred, so that it looks more like a blurry elephant. So that's how the everything can be. So motion changes, or any dynamics in the area of the picture, some part of being changing, that can be corrected by geometric calculation. And in here, eigenvalue, eigenvector, those kind of technique is very useful and very working just fine. Okay, so this is first part. Second part is about this stitching. So by this motion blur, that it can be extended, just saying it's more like the one camera is moving from one location to next location and the next location. So object doesn't move, just the camera moves, but they can be all different scene and different the sizes, so that can be taken care of by stitching and with the proper resizing and the redirection. So that's the next step about the stitching, image stitching, and the panoramic view. Okay, this is the part this chapter this chapter part is okay, they're done, and then we'll wait. We'll take some break and go to the next one. Okay.